When you think about AI, you probably think about intelligence, automation, and speed. You might think about chatbots, robots, or futuristic breakthroughs. What you probably don't think about is water. But here's the reality. Every time AI gets smarter, data centers get thirstier. And no, this isn't about servers asking for bottled water. It's about millions of gallons of water being used just to keep AI from overheating. AI runs on massive amounts of computation, and computation creates heat. Heat is the enemy of reliable systems, so data centers have to remove it constantly. Many of today's data centers rely on water-based cooling systems to do this. A common metric used is water usage effectiveness, or WUE, which measures how many liters of water are used per kilowatt hour of electricity. Depending on the design, data centers can consume anywhere from about 0.2 to 1.8 liters of water per kilowatt hour. That means a single large AI data center can use hundreds of thousands or even millions of gallons of water per day. Suddenly, your long shower doesn't look so bad. Most AI data centers cool themselves in four main ways. The first is cooling towers, where water evaporates to carry heat away from servers. This is efficient, but the water is literally lost into the air. The second method is chillers, which rely more on mechanical cooling and electricity, using less water on site but often increasing total energy demand. The third is liquid cooling, where water or coolant flows close to CPUs and GPUs to absorb heat more efficiently. The fourth is immersion cooling, where servers are submerged in specialized non-conductive fluids that pull heat away extremely effectively. The biggest water users tend to be evaporative cooling towers, which work well but can be especially problematic in drought-prone regions. Water consumption is only part of the problem. The other part is what happens after the water is used. Cooling systems rely on chemical treatments to prevent corrosion, mineral buildup, and biological growth. As water circulates, it picks up salts and chemical residues. Monitoring station where treated wastewater is discharged with sophisticated testing equipment and environmental monitoring systems. The shot shows the careful measurement and testing of discharge water with laboratory equipment and real-time monitoring displays showing chemical composition and safety levels. To keep systems functioning, some of this water is discharged as wastewater, known as blowdown. This blowdown can contain elevated salinity and treatment chemicals that must be carefully managed. It's not radioactive, but it's definitely not something you want ending up in your drinking water. The uncomfortable truth is that the AI race is focused on being faster, not more efficient. Bigger models, more GPUs, higher power density, and relentless scaling have become the norm. Faster AI without efficiency means more electricity, more heat, and more water. Efficiency is no longer a nice-to-have sustainability feature. It's a hard requirement for long-term viability. The most effective way to reduce water use is to reduce wasted computation. The cleanest watt and the cleanest drop of water are the ones you never use. This is where software efficiency becomes critical. Companies like MindAptiv focus on eliminating wasted computation at the software execution level. Modern cloud operations center with multiple screens showing resource allocation, server utilization, and automatic scaling in action. Operators monitor systems that automatically adjust resource allocation. The visuals show servers spinning up and down based on actual demand, with utilization graphs showing optimal resource usage. Their approach ensures AI systems do only the work that is actually needed instead of burning cycles unnecessarily. Less wasted compute means lower power consumption, less heat generated, and ultimately less cooling and water usage. Think of it as putting AI on a diet, same intelligence, fewer calories. Cast AI attacks the problem from the cloud infrastructure side by automatically right-sizing workloads. Sophisticated control room with real-time energy grid monitoring, showing power demand curves and intelligent workload scheduling. Operators coordinate AI workloads with available clean energy. Multiple displays show energy availability, carbon intensity, and workload scheduling optimization. Instead of running oversized servers that sit partially idle, Cast AI ensures applications use exactly the resources they need, no more and no less, reducing energy waste and cooling demand. Emerald AI focuses on power-aware computing by coordinating workloads with available energy. Their systems can shift or pause compute tasks to avoid peak demand, reducing strain on both the electrical grid and cooling systems. In simple terms, it tells AI, maybe now isn't the best time. At the physical layer, companies like Vertiv, Schneider Electric, and Johnson Controls are redesigning how data centers cool themselves. Liquid cooling, direct-to-chip systems, and closed-loop designs dramatically reduce the need for evaporative water loss. Microsoft has even announced data center designs that use zero water for cooling by relying entirely on closed-loop, chip-level cooling systems. That's not a future concept. That's happening now. If AI is going to scale responsibly, three things must change. First, efficiency must matter as much as raw speed. Second, water usage must be measured and reported transparently. Third, software efficiency and physical infrastructure must work together instead of being treated as separate problems. We need to start measuring compute per watt and increasingly compute per liter, because AI shouldn't outdrink entire cities. AI doesn't have to drain our natural resources to move humanity forward. With smarter software, better cooling technologies, and a shift from faster at all costs to efficient by design, the future of AI can be powerful and responsible. The real breakthrough won't just be how fast AI thinks, but how intelligently it runs.